everybody. The Fermi Paradox. That's the title of this year's James Marron Memorial Event. And the talk will be presented by Dr. Elias Aydi, Research Associate in Physics and Astronomy at Michigan State University. Dr. Aydi's subject is particularly appropriate because Jim himself was very inquisitive about why there is little direct evidence that other civilizations exist, when intuition from just looking up into a star-speckled sky would suggest that they might and should be out there in abundance. But what does the latest science, including recent revelations that there are certainly other Earth-like planets, have to say about the subject? You're about to find out. As noted, it's a question that Jim asked himself during at least one of the many talks he presented to GRAAA over many, many years. I think his membership, he and Evelyn joined the group probably around 1963 or so, less than 10 years into its existence. And those of us who have been around almost that long also realize that if it were not for Jim Marron and his wife Evelyn, Wien Observatory may never have come to be. That's something that some of your newer members or potential members need to realize. If it weren't for Jim and Evelyn, we might not have Wien Observatory, because as Jim was one of the leaders in the group in the 60s, he also, I don't know whether we got him drunk one night or something, but he decided that he was going to let us build his our observatory on his land. It was an offer he made, which was extremely generous, and I suspect more than once he and Evelyn regretted. He also was one of the major contributors to that monumental 5-year effort. Jim was amongst the principal block layers and was also the resident plumber. And the versatile Evelyn could always be counted on to support the hardworking crews in whatever capacity necessary. It often involved food and drink. All the ensuing disruptions to their lives they endured with tolerance and good humor that we will long be grateful for. That included selling 12 of their 16 acres to the association in 2017 for a very reasonable price. When we lost a person who could be aptly termed part of the soul, a yearly event that would honor James Marron. One of the highlight presentations each year is now designated as the James Marron Memorial Event. The goal is to feature a speaker with outstanding credentials, focusing on a subject that Jim would have held high interest in. Tonight, we hit the jackpot because Dr. Aydi, I'll get it right, is Research Associate in Physics and Astronomy at Michigan State University, as noted. He graduated with a master's degree from Notre Dame University at Beirut in Lebanon, which is his native land, in 2014. In 2018, he got his PhD in astrophysics from the University of Cape Town in South Africa. Elias's main research interests are time domain astronomy and multi-wavelength observations of explosive astronomical events, such as supernovas and merging stars. If we treat you well, maybe those are subjects for a future visit. He did say that he's enthusiastic about outreach and public engagement activities and has been looking forward to being with us this evening, even if it involved driving through a snowstorm. Dr. Aydi.
I may remove my mask. Is that okay? Thank you very much for having me here tonight. Thank you for the introduction. I'll try to stand in front of the camera so people can also see me on the Zoom. Hello, everyone. Thank you for joining us. So today the title of my talk is "Where is everybody?" And as David has said in the beginning, this is a question that a lot of people asked, whether they are astronomers or they are people that don't do astronomy but just look at the sky and wonder and look at these vast number of stars and say, where is everybody? But usually before I start any astronomy talk, I always like to introduce three parameters in the universe. And I know many of you are professional astronomers here, and a lot of the information that I might show might be very familiar to you, but please bear with me. And the first parameter I'm going to introduce is the distance, of course. So here in our solar system, of course, nothing here to scale, neither the sizes nor the distances. The sun, the star that we orbit, is around 150 million kilometers, or in the US, 93 million miles. And of course, this distance is on average because the Earth's orbit around the sun in an ellipsoidal path. So if you want to go outside of our solar system and get to the nearest to us, which is Proxima Centauri, we cannot see Proxima Centauri from the northern hemisphere. We can see it from the southern hemisphere. So I enjoyed looking at Proxima Centauri when I was doing my PhD in Cape Town. And Proxima Centauri is at a distance of 4 light years away from us. And we jumped immediately to use another unit, which is the light year instead of miles or kilometer, because the distances just become so big. And light years is the measure of the distance that is traveled by light during 1 year. So light, the fastest speed we know of, 300,000 kilometers per second. And this is the distance that the light travel in 4 years, for example. So any light that we are receiving now from Proxima Centauri has already left Proxima Centauri 4 years ago. So every time we look at Proxima Centauri, we see how it was 4 years ago. And vice versa. Proxima Centauri has a planetary system around it, which was discovered recently. There are around 7 planets around Proxima Centauri, 2 of which might be habitable. We'll talk later about what we call a habitable zone, but 2 of which might be habitable. We know that there might be no intelligent civilization on them, but they could host life. And now let's imagine together that there's some kind of an intelligent civilization on one of these planets, and looking straight to Earth with a very giant telescope. And what they will see is, if they are looking right now at our planet, they won't see a planet that is ridden with a pandemic and we are all struggling with a pandemic, wearing masks. But what they will see, instead of people walking street with masks, we'll see how our planet was in 2017, 4 years ago, when people were living not aware of the great danger that is coming in around 3 years. Of course, the sky is full of stars. It's this very beautiful picture. I really love it. You see the Milky Way. And let's now pretend, or let's now imagine that there is a star at a distance of 51.92 light years away from us. And also around this star, there's a planetary system with one of the planets hosting life and hosting intelligent civilization with a giant telescope, again, looking at Earth right now. What will happen is that they will see how Earth was 51.92 years ago. Why 51.92 years ago? Because this will bring them back to the 20th of July, 1969. And if they point their telescope towards the moon instead of our planet, they will be able to see Neil Armstrong putting the first human step on the lunar surface right now. I hope they will record it. They will send it back to us 52 years in the future. They will be able to debunk all conspiracy theories about the lunar landing. This is our galaxy, the Milky Way, or an artistic impression of our galaxy. Of course, we cannot take photos of our galaxy because we live in it. The galaxy is 100,000 light years across. So if we, again, the light needs around 100,000 years to travel from one side of the galaxy to the other. Or if you have a ship that can travel in the speed of light, hypothetically, we know that we cannot travel in the speed of light based on the physics that we know of. And if we have this ship and we want to travel from one side of the galaxy to the other, we need 100,000 years. We've left our galaxy and we want to go to the nearest galaxy to us, Andromeda or M31. Andromeda is at a distance of around 2.5 million light years away from us. The distances just became astronomically bigger. Again, now we want to hypothetically suppose that there's another intelligent civilization living around one of the stars in Andromeda. And also they have a much larger telescope, and they use this telescope to point it towards our galaxy, particularly towards our star, more particularly towards our planet Earth right now. If they manage to do that, this is what they will see. They won't see any of us modern humans roaming around the planet. What they will see is Homo habilis, one of our early ancestors. Homo habilis means the handyman because it's one of our first ancestors that started to use tools throughout the evolutionary history of our species. They say that a picture is worth 1,000 words, and I could have maybe summed up all the stuff that I said right now with just one photo that I'm going to show you. This photo that I'm going to show you, I think, is one of the most inspirational photos that has been taken in astronomy. And this photo was taken by the Hubble Space Telescope, which was pointed for continuous month, taking photos of the same patch of the sky, this very small patch with no much stars in it. This is a comparison of the size of this patch in the sky to a full moon, just for scale. And as I said, they pointed the Hubble Space Telescope and started getting data and images of this small patch of the sky. And after combining all this data that they are worth of months of observations, this is what they got. It's called the Hubble Ultra Deep Field. And each or most of the dots that we are seeing in this photo is actually a galaxy on its own. Some of them billions of light years away from us, not millions, billions of light years away from us. Some of these galaxies are much bigger than our Milky Way, some are smaller, but I think this photo is just always implies a sense of humbleness when I look at this photo, because really it shows us how massive the universe we live in. This small patch of the sky has this much galaxies. The observable universe, as far as we know, is 93 billion light years across. Again, this is an astronomical large number, and I don't even try to comprehend, but this is what we think is the observable universe. Could the universe be bigger? Could be, we don't know. Now, the second parameter that I want to talk about is the numbers. And we already saw that the numbers are really big when you're talking about the universe and astronomy. And again, this is our Milky Way, an artistic impression of our galaxy. Our Milky Way has around 200 billion stars in it. So that's 2 followed by 11 zeros. And the observable universe has around 100 billion galaxies on average. As I said, some are bigger, some are smaller. So if you want to imagine the number of stars in the universe, observable universe, we just have to multiply 100 billion by around 100 billion. The number we get is 1 followed by 22 zeros. This is a rough estimate of the number of stars in the universe. Some of you might even know this number, but I don't know what 1 followed by 22 zero is called. The last parameter I'm going to talk about is time. And on Earth here, the average human being life is around 80 years, 70 to 80 years. And that's what we are used to when we talk about time in our daily life. We use hours, minutes, seconds, years, maybe centuries. But when we talk about the lifetime of stars, we directly jump to millions and billions of years. This is the life cycle of a star like our sun, and our sun has been around for around 4.5 billion years since its birth. And our sun will stay around for another 5 billion years before it starts dying, losing its outer layers to turn into a white dwarf. When this happens, the sun is going to turn into a red giant at some point. It's going to swallow Earth and the inner planets, but this will only happen in 5 billion years from now, so don't worry about it, we won't be here. The universe has been around for around 13.7 billion years since the Big Bang, and again, this number is just so difficult to comprehend. The title of this talk today is Where is Everybody? And usually when we want to look for other civilizations outside of our solar system, we want to find other planets, or what we call exoplanets. Exoplanets are planets that are hosted by stars outside of our solar system. And there are multiple ways that astronomers use to find exoplanets or to search for exoplanets. Today, I'm going to talk a little bit about two of these methods that astronomers use to find exoplanets. One of them is called the transit method, and the other one is called the radial velocities. And we're going to start with the transit method. And just from the name, I think most of you have guessed what does the transit method mean. So we monitor a star, we monitor the brightness of the star, and we wait to see a certain dip in the brightness of this star. If we see a dip in the brightness, even if it's a very small dip in the brightness, this means that there's something has blocked the light that is coming to us from the star. And this could be an actual planet just transiting or traveling in front of its host star. If this happens to repeat again and again and again, then we can confirm that yes, there is some planet here orbiting around its host star, passing in front of it and causing a small dip in the light from the star. Based on this dip alone, we can learn a lot of stuff. From it, we can learn the year on this planet, what we call the orbital period. So how long it's taking this planet to make one complete orbit around its host star. Based on the shape, we can tell a lot about the radius of the planet, if it has an atmosphere or not. So just from this dip in the brightness, we can learn a lot of information on this planet and even its host star. Sometimes we have more complicated examples. This is an example of a system called TRAPPIST-1. So this is our real data. And here I'm showing a dip that looks a bit complicated. And this is because this dip was not by just one planet, but by 3 planets. So here we have more complicated transit, but the astronomers has managed to develop the tools now that can disentangle transits that are happening due to multiple planets orbiting their host stars. So we don't only discover single planets, we discover planetary systems. It could be even more complicated. So this is another example. These are real data, and we see multiple dips, each from different planet, doing an orbit around the host star and transiting in front of it. The master of finding these planets, or the game changer, was Kepler, not the scientist, the mission. So Kepler was a NASA mission that was launched in 2008, I think, and was operational from 2009 to 2018. And during this 9 years of operation, Kepler found more than 2,660 exoplanets. Most of them were found by the transit method, of course. So Kepler was just monitoring a lot of stars in our solar neighborhood, just checking how the brightness of this star is changing with time. And if we see a dip, it means that there could be potential planets. And then the astronomers work on confirming the presence of this planet. The successor of Kepler is TESS, the Transiting Exoplanet Survey Satellite. Again, similar to Kepler, TESS, which was launched in 2018 and still one of the major operational satellites to find exoplanets. And TESS cover a large part of the sky. They do it in different semesters. So half a year they observe the northern sky and then go to the southern sky and back and forth. And some parts of the sky, they will have almost full year of coverage. And some other parts of the skies, they can be covered by around 27 days or a month. But still, this means that we have a large number of stars that are continuously monitored to see any change in their brightness. The main aim of TESS was to find what we call Earth-like planets, so rocky planets that are in the habitable zone of their host star. When we say a habitable zone, it means that the planet is not too close or not too far from its host star. Because if it's too close, it means it will be too hot, and therefore it's difficult to support life. If it's too cold, again, it's too far, it means it's too cold. So again, it's difficult to support life. So there's this sweet spot that we call the habitable zone or Goldilocks zone. And this is the spot around the star where it's not too hot, not too cold, which means it could support life. And TESS particularly tried to find planets in this habitable zone. So far, TESS has confirmed more than 170 exoplanets. And there are thousands of candidate exoplanets that has been found by TESS. When I say candidate, it means that we might have found only one brightness dip from this star. And therefore, TESS will put out this data and ask astronomers to use ground-based telescopes to follow up on these stars and check if this dip in the brightness will repeat. And then we can confirm that there is a exoplanet. And this is not only for professional astronomers to do, even high school students with I would say not very expensive telescopes could also follow up on exoplanets candidates and confirm them. And actually at Michigan State, we have the campus observatory, a small 24-inch telescope that our undergrad students use to follow up on exoplanets, and they have confirmed multiple ones. Now I'm going to jump to the other method that we use to find exoplanets, which is radial velocity. I know many of you might be familiar with this concept, but just to talk a little bit about in details about radial velocity. So radial velocity is a concept that relies on the Doppler effect. So Doppler effect is the effect of the change in the wavelengths of a certain wave when it is emitted by a moving object. Let's take an example. We have an ambulance and you are standing on the side of the road. When this ambulance is traveling towards us, we hear that the pitch of the sound is changing when the ambulance is coming towards us, and then when it goes away from us. This reason in the change of the pitch of the sound from the ambulance is due to a change in the wavelengths of the sound wave. Because when the ambulance was coming towards us, what happened is that the wavelengths of the waves get compressed, and therefore the pitch of the sound, because the frequency of the sound will change. And then when the ambulance is going away from us, these waves starts to get elongated, and therefore the wavelengths will get bigger, and the sound pitch or frequency of the sound will change. Similar to sound waves, also this happens with light waves when we are receiving light from a moving object, could be a star or any moving object. But before talking about the change in the frequency of the light or the wavelengths of the light, when you have even a star that is maybe orbiting another star, we see also a change in the frequency of the light or the wavelengths, because even this small rotation of the star around the center of gravity of the system will cause a certain shift in the wavelengths of the light when the star is coming towards us and then going away from us. We call this redshift and blueshift, and I'll explain why we call them redshift and blueshift. This is the electromagnetic spectrum that we are familiar with, and here we are seeing all the waves from gamma rays to radio. And of course, the shorter waves are known as the high energy waves, or the gamma rays, the X-rays, and then the lower energy waves like the radio or the longer waves. This small part here of the electromagnetic spectrum is what our eyes can see. We call it the visible light. And this consists of all the colors that our eyes can see, from the purple or the violet all the way to the red. And in the visible spectrum, These waves are the shorter waves. So the bluer waves, the violet waves are the shorter ones, and the redder waves, the orange or the red, are the longer one. So when a light gets elongated, when it is emitted by an object that is moving away from us, the wavelength of the light becomes bigger, and we say it's redshifted. Why it's redshifted? Because the wavelength is getting bigger, which means it's moving to the redder waves. And when the light emitted by an object moving towards us gets compressed, the wavelength gets shorter, and we call it blue shifted because the light is moving towards the shorter wavelengths, which are the bluer ones. Can we measure this shift in the light when it's emitted by a moving star or moving object? Yes, we can. And in order to do that, we need to spread the light that we are getting into a spectrum. And this can be done using a spectrometer or a spectrograph. It's like a prism, actually, which works on spreading the light coming from a light source into a spectrum. Now, when we have a light going through a prism, we see this, what we call a continuous spectrum, which is the spread of the light into all the colors. But when the light goes through a cloud of gas or container containing gas, and then go through the prism, we see that the light that is arriving on our detector is missing some of the colors. These we call absorption lines, and they are caused by the molecules of this gas or the atoms of this gas here, absorbing some of the colors, very precise colors. So we see that the continuous spectrum is missing some of the colors. And this also happens when we are receiving light from a star. The light coming from a star will travel through the atmosphere of the star, and the atoms in the atmosphere of the star will interact with this light and absorb some of the colors in the spectrum. So when we receive this spectrum here on Earth, we see that it's missing some of the colors, very specific colors. But since we can do this in the lab as well, we can experiment with different gases like helium, hydrogen, oxygen, you name it. And we can see each one of them, which colors, which precise colors they will absorb. So by repeating this experiment in the lab, we can see, for example, that spectrum of sodium, we will lose these particular colors. Spectrum of mercury, we lose these colors. Spectrum of lithium, we lose different colors. And since we have spectrographs that can measure the wavelength of the light digitally, we can now have an idea exactly of the color, not just a color, but we can give it a number. And once we can give it a number, we can identify a long list of missing colors due to different gases like hydrogen, helium, etc. All we need to do is observe the star again and see what colors are missing, compare them to what we got from the lab, and therefore we can identify which atoms are present in the atmosphere of the star. So when we usually say that we found hydrogen or helium or carbon or oxygen, etc., sodium in the atmosphere of the star, this is not coming from nothing. We are not like just predicting that there's something there. We actually see the missing colors from the light that is coming towards us due to the presence of these certain atoms or elements in the atmosphere of the star. So basically, we can tell from this method the chemical composition of the stars, of the galaxies, of the universe. But again, we're going back to the example when we have two stars orbiting their center of mass. We call them binary system. And if these two stars are moving towards us and then away from us and then towards us and then away from us, we're going to see a shift in the light. So instead of seeing these absorption lines where we expect them to be, we see them a little bit shifted to the right or to the left or to the blue or to the red. And therefore, instead of seeing this color missing right here, for example, from atoms of hydrogen, we see it either a little bit red shifted and then blue shifted and red shifted and blue shifted. This not only happens when we have two stars orbiting each other, but also if we have a planet orbiting around star. All of us think that our planets are moving around the sun in orbit, but actually the planets and the sun are moving around the center of mass of the solar system. And if we take just, for example, Jupiter and the sun, the center of mass is outside of the sun. So the sun, what we'll be doing is just wobbling in its place around the center of mass. However, the other planets will be doing, of course, a larger orbit. But this small wobble of the sun around the center of mass of our solar system will cause a slight shift in the light from redshift to blueshift. It's very small, much smaller than what we see when we have two stars orbiting their center of mass. But now we have what we call high resolution spectrograph that can even detect this very small shift in light due to the presence of one planet or more than one planet around their host stars. And therefore, we'll be able to measure the shift of the light. If it keeps happening and repeating, we can confirm that, hey, there's a planet around the star. And of course, now we managed to develop the techniques that can disentangle the presence of more than one planet just using the radial velocity method. Between radial velocity and transit, scientists have confirmed more than 4,800 exoplanets to date since 1992, the date of the discovery of the first exoplanet. And this number, of course, is changing on a daily basis. So this number in a month from now would be larger. Of course, these are the confirmed exoplanets, but using this number now, we know that most of the stars in our galaxy and in the universe have planets around them. And therefore, we can estimate that there are several hundreds of billions of exoplanets in our galaxy alone. We're talking about several hundreds of billions. And this what made Enrico Fermi ask his question in the first place. Because even before we found the first exoplanets in 1992, astronomers and scientists knew that there is nothing special about our solar system and that there should be planets around most of the other stars in our galaxy. And just by the number of stars, we can expect there should be billions of exoplanets in our galaxy alone. So Enrico Fermi with some friends asked a few questions that there are hundreds of millions of stars and planets in the galaxy and in the universe in general. And we know that there should be some of them, like a fraction, few billions of them are Earth-like planets. So planets in the habitable zone that could support life. And let's say also there's a fraction of them that managed to, on a fraction of them, we have intelligent life that managed to evolve. This means that our galaxy and the universe, there should be a lot of intelligent life, and some of them might even manage to master interstellar travel. And therefore, Enrico Fermi asked, where is everybody? Where are all these civilizations that should be now roaming our galaxy and maybe invading us? So, but still, we haven't found any. And this later has been known as the Fermi Paradox, but I won't call it a paradox. We have some, answers, or like we can think about some answers why we haven't found any or why no one visited us yet. But before doing that and having a discussion together, I would like to differentiate between two terms that we're going to use now, which are life and intelligent life. And we're going to start about just the word life, which could mean anything from intelligent life to single cell organisms. And when we're talking about single cell organisms, I think this is very easy to get on the planet, because we are oxygen, carbon, hydrogen, nitrogen, and a few other elements. And these elements are very abundant in the universe. The Big Bang started with a very large expansion of space, and at some point around 400,000 years after the Big Bang, there were mainly hydrogen and helium. And one might think, where did all the other elements that we know of, that we know in the periodic table of elements, come from? Well, I'm sure most of you know the answer, which is the stars. So the stars, back, we'll call that like first population of stars, after the Big Bang, after the recombination era, we have stars that started to form. They're mainly formed from hydrogen, helium, and some deuterium. And then these stars started forging heavier elements like carbon and oxygen in their cores. And because they were so heavy, they started exploding in what we call supernovae. And during these explosions, they formed much more elements that they spread into the universe. And then newer population of stars started to form from the remnant of these stars that are enriched with heavier elements like carbon, oxygen, etc. So basically, even the elements that exist in our body are all coming from stars like that has exploded millions of years ago. So when we say we are all made of stardust, this is not cliche. As I said, every atom in our body comes from a star that died billion years ago. And what is fascinating is that the atoms in our right hand could be coming from a different star than the atoms in our left hand. I find just I always give a talk that's called Our Ancestors. I'll be talking about just the stars because they are really our ancestors. We are just the newly born species that has formed from the stardust. Now on Earth, since the formation of our sun and then our planet, it took around 1 billion years for single cell organisms to start to appear on our planet. And this is not a very long time compared, for example, to the age of the universe. And therefore, given the large number of exoplanets that we know of, we're talking about hundreds of billions. And given that we know that many of which would be in the habitable zone, so they could support the form of life that we know of. And since the basic ingredients of life are very abundant, thanks to the supernovae and the stars forging elements in the core, it should be that everywhere in our galaxy. And when people ask me, do you think that there's life out there? I'll say, definitely. When we're talking about basic form of life, it should be out there. Our planet is not special. And there should be a lot of like our planet in our galaxy, and there should be life evolving on these planets. Actually, I'm going to make a bolder statement and say that we'll be finding in the next 10 years or so life in our solar system, not even outside of our solar system, an exoplanet, maybe around one of the moons, maybe on one of the moons that orbit Saturn or Jupiter, particularly this one over here, Enceladus, that I think has great potential of hosting basic form of life. So if in 10 years from now, NASA announced that they found life on Enceladus, remember my talk. Now we'll be talking about intelligent life. I'm not sure how intelligent we are, but let's say intelligent life. This form of life is a bit different. It took longer for life to evolve into an intelligent form since the first single cell organism that appeared on our planet. It took actually around 3 billion years for life to evolve on Earth. And actually some stuff happened on Earth that would make us think that could it be that the intelligent life on Earth a special one? Because during this course of evolution, there are some improbable events that took place on our planet that led to us being here now. The first event happened 65 million years ago when the dinosaurs were still roaming our planet between 250 and 65 million years ago. And mammals looked like this. They look like small rodents, and basically they couldn't flourish because of the presence of these gigantic creatures on our planet. But again, 65 million years ago, something happened, which we all know of, which is a giant asteroid or comet, hit our planet somewhere near Mexico now and caused the extinction of land dinosaurs, because we know that some of the flying dinosaurs survived. And one might think that maybe if this extinction event did not happen, maybe mammals wouldn't have been able to flourish, and therefore it could be possible that us wouldn't be here now. I know a lot of people think that no, there could be a chance that mammals would have evolved to what we are now. Yes, it could be, but it could have been delayed by 1 billion years. No one knows. So us being here now is thanks to this comet. The other improbable event that happened is more recent, actually, and is directly related to our evolution from the great apes. And this event happened in a time where the great apes around the planet were still living on trees. This is our early ancestors. They were still living on trees, whether in Africa or in Asia. But something happened on the eastern side of the African continent. It's called the East African Rift. This rift caused, because of the clash between different tectonic plates, it led to the formation of giant mountains on this side of the African continent, blocking a lot of the rain from this area here. So this area here became very dry, and the forest started gradually to turn into savannas. This forced the creatures living on the trees over there, like our ancestors, to leave the trees and start roaming the savannas. But it's very dangerous to walk around the savannas on 4 legs, because, or on 2 legs and 2 hands, because it would be difficult to see any prey that it's coming toward you. Also, it's very difficult to cross large distance on 4. So our early ancestors, because they were forced to start roaming the savannas, they started walking upright. And this was a major change in the course of our human evolution, because when humans started walking upright, they started using their hands more into more creative stuff like tools and inventing fire. And because of this, because of the use of tools and the invention of fires, our brain started to evolve much faster than our cousins, like the orangutan and the chimpanzees. And therefore, this African rift played a major role in the course of our evolution. And all the species that are related to our evolution can be found in this region in Africa. Most of the specimen that has been found and they used to assemble our evolutionary history has been found in this region of the world. And you can see that the brain of these our ancestors start to grow bigger and bigger with time until we reach what we call Homo sapiens, or the modern humans. So thanks to this rift, the great apes of the eastern side of Africa turned into something like us now. However, the great apes in Southeast Asia has evolved into orangutans, and therefore they are still living on the trees, because no major changes in the climate happened in Southeast Asia that forced the great apes to start walking upright. And therefore, this is a very improbable event that led to the evolution of our species, an intelligent species. Again, I know that it could be very possible that our species would have evolved into something more modern from the great apes, despite, even if like the East African rift did not happen, but it could have took much longer. We are now seeing that the chimpanzees, the orangutans, they are getting smarter, maybe their brains are getting bigger, but it could be that in millions or billions of years that our brain could have reached something that reached our current state, if not for the East African rift. So again, it is really a reasonable question to ask, is the life on Earth special? But I still think it's not, despite these like improbable events that led to the evolution of a kind of intelligent species on our planet, given the vast numbers, the hundreds of billions, which is number very difficult to comprehend, of exoplanets in our galaxy, there should be life out there. And the question comes back again, where's everybody? So I'm gonna list now a few explanations for where's everybody. And I would like to hear your thoughts as well after I list these explanations. The first one is that it could be that there are life out there, a little bit modern, but not advanced enough to communicate or maybe master interstellar travel. The other one is that intelligent life doesn't last too long. And I think this is now currently one of the main explanations for why we didn't find anyone, is that intelligent life that doesn't last too long. And if we want to compare just on our example here on Earth, we can tell that the technological advance grows much faster than the moral advances. And therefore, it could be that intelligent life is always doomed to self-destruction. And if this is true, it means that an intelligent life will last for a few thousand years and then it will disappear. And when we think about a few thousand years, it might be a long time, but actually it's fractions of seconds compared to the entire lifetime of our universe. If you want to fit our universe into one calendar year, you can see that the universe started on January 1st. This is when the universe started. This is the Big Bang. Our Milky Way started to form in March, 3 months later. And then now in August, already past half of the year, our sun started to form, and only in November. So this is the 11th month of the cosmological calendar year. The first multicellular organisms started to form on our planet. Now we're gonna go all the way to the 18th of December. So we're already in the last month of the year, 18th of December, early land plants started to appear on our planet. I want to fast forward to the Christmas Eve, 24th of December, when the dinosaurs appeared. And then first mammalian ancestors appeared, so just a day later. And then all the way to the 29th of December, our glory day, when the planet was hit by a giant asteroid and the dinosaurs suffered. And then now we are on the last day of the year, 31st of December at 10 a.m. Apes start to appear. At 9:24 p.m., just a few hours before midnight, first human ancestors start to walk upright. Now we are at 11:54 p.m., 6 minutes before midnight, anatomically modern human appears, so Homo sapiens. 11:59:45, invention of writing. 11:59:50, 10 seconds before midnight, pyramids were built. And then 1 second before midnight, the voyage of Christopher Columbus started. So the modern life that is capable of space exploration and communication that we know of here on Earth is less than a fraction of a second compared to the lifetime of our universe. So now if we want to go with this hypothesis that an intelligent life doesn't last too long, so it will appear for a second compared to the life of the universe and then disappear, another one appear and disappear, another one appear and disappear. There's a small probability for two intelligent life to coexist. Actually, I did some calculations just to check the probability of just two intelligent life to coexist during the lifetime of the universe. It's 1/31 million for two intelligent life to coexist. But again, there are 100 billions of planets, so there could be millions of intelligent life coexisting, and therefore this probability would be bigger. The other reason why we couldn't find anyone is that the universe is too big. This is, our galaxy alone is 100,000 light years across. So we said, if you want to travel from one side of this or the other side of the galaxy in the speed of light, is going to take us thousands of years. Even if we want to send a message, if we want to send a message to Proxima Centauri, the nearest star to us, it's 4 years. So they receive our message, hi, 4 years after, and then they reply, hi, 8 years after, we receive the hi, how are you? And after, I don't know, 16 years, we'll just introduce ourselves. And yeah, it takes a lot of time. So the universe is too big. And a lot of us think, okay, but we as a human has been leaking a lot of radio signal into our galaxy. And that's true. We've been leaking radio signals since the early 1900s. To be more accurate, November 1920, when the first radio broadcast been sent from Pittsburgh. And we've been leaking radio signals since then. Do you know how much this radio signal has been traveling? Because a lot of people like to say, definitely some intelligent civilization would pick up this radio signal and would know that there's some intelligent civilization on a different planet. But if we look at our galaxy, this is how much the radio signal has traveled. Not this square, no, this point here, the blue point, blue dot here. You can't see it from my laser. This blue dot here is how much compared to the size of our galaxy. The radio signal that we have been leaking for 100 years now. So imagine if, say here, maybe inside the box, but just here on the other side. Would they have picked up our signal? Of course not. So yeah, our galaxy and our universe is too big for us maybe to communicate using the speed of light. Also, we haven't been listening to for too long. This here, I'm showing a picture of these antennas or radio telescope from the SETI experiment, the search for extraterrestrial intelligent life. And these dishes are actually pointed towards the sky and are listening to any radio signal that could be coming from intelligent life. So far, we haven't found any, but we only have been listening for like 20 years or so, a little bit more. So again, this is nothing compared to the lifetime of our galaxy or the universe. And it could be that no one is transmitting. I mean, we are anticipating a signal, but it could be that no one is transmitting. And they could be also not interested at all. They could be there, but just not interested. We are too, I would say, basic for them. Why? I mean, let's take this example. If you are driving on the highway or if you're walking on the side of the street and there's some ants that are doing their normal work on the sidewalk, would you stop, introduce them to your technology? Definitely not. We're gonna step on them and then continue walking. So I would say it's better if they don't discover us, honestly, because based on the history of our species, when a slightly more technologically advanced civilization visit a less technologically advanced civilization, it's usually not good. It's not good news for the less technologically advanced civilization, unfortunately. So if they have the same morals as us, it's not going to be good news for us. The other one is that they could be just too alien for us to recognize that this is a life. I mean, always when we think about aliens or intelligent lives, we give them eyes and ears and nose, and they look somehow like us. But they could be a form of life that not even recognizable for us that this is a form of life. We know of only one form of life here, that's it. But there could be other forms of life that are not recognizable to us. And therefore, they could be just too alien for us, or it could be too classified. Of course, I don't believe that, and we can talk more during the discussion why I don't believe it's too classified. And the last one is that we're just alone, which brings me to the last slide of my talk. It's a quote by Arthur C. Clarke, who say there are two possibilities. Either we are alone in this universe or we are not, and both are equally terrifying. Thank you so much.
Thank you, Dr. Aydi. We are going to do a hybrid of questions as we did in the presentation. And Chris and I are going to tag team together. I'm going to first of all ask for a few questions from the assembled audience, but you people out there in Cyberland, you're not going to have to wait till we go through all of these because we'll try to alternate somewhat between questions or comments, being that it is a pretty interesting subject that not everybody would agree to. And therefore feel very free to be candid with us because that's what science is all about. Let's start with a hand out in the audience, speak up or come down here maybe. Are you willing to do that? And ask your question or ask it so that it can be heard.
I will repeat the question. You can ask it.
Oh, okay, ask it and repeat it. That's great.
Definitely I would like to hear any hypotheses or ideas about why we haven't found anybody from the people in the audience here or online. Yes.
Yeah, so there's an intelligent life on a planet somewhere nearby, 10,000 or 10 light years away. Would they be able to, how do we communicate with them? Because you got a time problem, but you also have a brightness problem, don't you? I mean, the sun's pretty bright, but it'll just look like a tiny star to those folks that are 10 years away. And we could not hope to generate enough brightness in our messaging to even, be seen that way.
So yeah, that's a very good point. The sun is very bright in the visible light, but it is less bright in the radio wavelengths. And therefore we might be able to generate enough radio transmission that could be recognizable or differentiated from the emission from our sun. And this is what we usually do also when we're studying distant objects, is that we look for a type of radio waves that we are unfamiliar with, that we don't have a natural explanation for. So now there's a very hot topic in astronomy where we talk about fast radio bursts. They are called FRBs, or fast radio bursts. They are bursts of radio emission coming from distant galaxies that we are not sure what is the origin of this emission. There's a lot of hypotheses, and some suggest that they're coming from magnetars, and I think this might be the most plausible explanation now. But yeah, this is type of emission that we are unfamiliar with. Other type of radio emission from star explosions or AGNs, active galactic nuclei, we are familiar with now, and we are able to differentiate them. And I hope that an intelligent life that managed to master at least communication with other intelligent lives be able to differentiate between a natural radio signal from a star or unnatural radio signal from an intelligent life. Yes?
In your opinion, what do you think UFOs are?
So the question is, in my opinion, what do I think UFOs are? Well, as most of you know, UFOs stands for unidentified flying objects. So I think they are unidentified flying objects. And this is well, it brings me to what I said. It's too classified, and I was joking about it. Yes, I'm joking about it because why they are unidentified, it's because usually they are spotted by people who are not very familiar with the night sky. So who are the people that look at the sky the most? They are the professional astronomers and the citizen scientists or amateur astronomers, and maybe citizen scientists look at the sky more than professional astronomers nowadays because we sit more in front of our computers now. But these are people who are very familiar with the night sky. What are the reports of unidentified flying objects between citizen scientists and professional astronomers? Almost zero, I would say. Why? Because they know what they are looking at. However, people who are not expert in the field, they might be jumping to conclusions directly, usually conclusions that us professionals would not jump to. And I'll give you an example. It's a very famous example, I think from Arizona. There was a police car that was following a very bright light in the sky. And there was reporting that, hey, it's moving, we think it's aliens or an invasion or whatever. Turned out to be Venus. But the police officer was so much absorbed by what he was seeing, the road was very curved. So he was driving on a curved road and he was thinking that the object was moving, not focusing on his driving, that he was actually moving a lot. And this is just Venus and not some alien ship or something like this. So it's usually these unidentified objects reports come from people who are not very familiar with the night sky. A lot of people ask me, so what about the new Pentagon videos that they have declassified recently? And they said that there are not new Army technologies that are classified. I would say that there are new Army technologies that they are classified for sure. Of course, they are not going to say because the Army cannot, because there's safety of the Army here, and definitely they cannot declassify such information to other countries. So I'd say, yeah, there are just new technological.
We got one coming in.
Sure.
Well, it was just like on-scum planets are more likely than higher technological life. Your opinion, I think it was a comment to say pond scum planets are more likely than higher technological life. And I think you would agree. That's your presentation saying that.
Exactly. I think yeah, the higher technological life. I mean, I know it's more of a joke from the comment, but I kind of agree. Yeah.
How about one more from the chat?
Didn't have any. No, I didn't have one. Well, one was that they wanted the sound was terrible, and I said it will be recorded so that they can
There were
pick up on it.
questions from someone like that. Yeah.
So we talked about unlikely events during manage
hey, it could be like a place where the conditions for life as we know it are too harsh, but still life managed to evolve. And this is one of the examples, as I showed, Enceladus, this moon around Saturn, which has a lot of oceans of methane. And this methane ocean, under surface methane ocean, although the condition there is very harsh, they could cause life, similar to what we have here on Earth. So that's why we have a higher chance to find life even in harsh conditions. Yeah, sorry. Yeah.
Briefly spoke about frequency, and you briefly spoke about us transmitting information.
Radio, yeah.
So when I read articles on what study of NASA everybody's getting back, it's very vague. So my question is it possible that this is a warped echo frequency that's coming back at us from what we're saying, or just a frequency altogether because there is frequency?
Right. It's a very good question. So if we receive frequency from us, probably would be able to recognize it. That yes, we recognize it, that this is not a natural frequency. And so far we have not found unnaturally explained frequency other than fast radio bursts of FRBs, which now there are natural explanations for them, but we know for sure that these are coming from very distant galaxies. Initially, they were thinking, oh, could these FRBs or fast radio bursts coming from here, from Earth? Then they started ruling out all the possibilities, and now we know that they are coming from distant galaxies. So yeah, there could be some confusion, but I think we'll be able to rule out this time that, oh, is this coming from us or not? Yeah, but this is reminds me of a very funny story where I'm trying to remember the exact observatory, and now I just can't remember the exact name. There was this radio telescope. Usually they build radio telescopes in the middle of the desert as far as possible from any radio transmission, Wi-Fi, cellular, everything. And they started detecting this weird radio signal on this telescope, and they couldn't find any like explanation for it. And they started thinking, oh, could be alien here, like what is that? But then they noticed that the telescope is only detecting the signal when it is pointing toward one direction. They were like, okay, probably we're getting this emission from this part of the sky. And they were like, no, actually, it's like on a lower elevation. Then they thought more, and they were like, oh, okay, actually, we're getting this emission or this transmission when we are pointing the telescope toward our kitchen. Because what was happening is that one of the astronomers was opening the door of the microwave before it ends. And therefore, we have this burst of microwaves that is detected by the telescope. And they ended up putting out a small paper about it that, hey, the aliens that we thought that we discovered were our microwaves.
So that's kind of where it's going to.
Exactly.
We're putting out information, and then we have the gamma rays.
Right. So try as much as possible to avoid being in a, so they don't put radio telescopes in a city, of course, put it as far as possible from cities. And we are getting better at finding out if it's coming from us or not. Yeah. Sure.
You showed us that small spot in our galaxy that is as far as our radio signals would have gone so far. And, we're hearing these, pretty substantial numbers about, how many planets would be in the habitable zone. But it seems like the question about other life is more about how many of those planets are in that little circle. How many of them have heard our first hello and not, let alone had time to say hi back to us?
Sure, that's a very good question. Honestly, I don't know the number. I try to go back to this photo. Right. So, oops, no, we passed it. Sorry, it's moving in delay on my side. Yep. So the question would be, how many planets are in 100 light years away from us? Because we know that we started transmitting in around 1920, so that's almost exactly 100 years ago. So how many planets are there in 100 light years radius around us? And
That we have.
that might be in the habitable zone, or I really don't know the number. That's a good thing to look at. Stars in our solar neighborhood has been studied extensively, and missions like Kepler and TRISS try as much as possible to study stars in our neighborhood. They are now focused a lot on these dwarf stars in our neighborhood that could have like rocky planets around them. But how many of exoplanets has been found in 100 light years radius around us, and how many of them could be in the habitable zone? I definitely know of two, which are the two planets in the planetary system around Proxima Centauri, which is the nearest star to us, 4 light years away from us. We know that there are 2 planets in the planetary system are in the habitable zone. How many more? I really don't know. So if there's a intelligent life on one of these planets in Proxima Centauri, they would have picked up our signal in 1924.
So we've gone from the huge number of possible lives out there to the 2 that we.
I mean, 2 that I know of. There could be more, but I really don't know the names or like which planets might be. Larry, do you have an idea about how many planets are in the 100 light years solar neighborhood?
Well, if you simply say the nearest star is 4 light years, that's a typical distance, then 100 light years divided by 4 makes volume,
Right?
gives you 16,000 stars to play with.
Of course.
And you know, there's a few planets at least for each of those 16,000.
Right.
The question is, what fraction of planets are in habitable zones? So take your 16,000 multiplied by that fraction, you get
Right.
the rest of that.
Exactly. And given that the solar neighborhood is homogeneous in stellar density, which should be is. Yeah, that's a good way to estimate it.
So what fraction would you say are in the habitable zone?
So I don't know what fraction of planets that we know of are in the habitable zone, because that's the factor that we need to know to multiply 16,000 stars. And yeah, I don't know how many planets, because the number keeps changing every week. From the 4,862 exoplanets that have been confirmed, I don't know now. We can Google it in a second, but yeah.
2 more questions. Mark's got his hand coming right, or his arm coming right out of his socket.
So I have a question. So let's say we got a signal, we said, yes, it's alien. What would your response be? Or what is our answer? And is there a
Hide.
government agency, or scientists working on, what would you do at that point?
I mean, the Space Force has been established a few years ago. I wouldn't recommend trying to contact them back, to be honest, just for the reasons I mentioned earlier, that if they are more technologically advanced than us, could be bad news to us. A lot of scientists that are in the field would think that it's better not to try. I mean, it's very tempting, and yes, we want to communicate with other species. Could be, I don't know, could be bad news for us. So yeah.
One more.
Yeah.
Is there one more?
What would you do if you were able to go to Saturn's moon level to support life?
Oh, that's a very good question. I mean, that might,
Repeat that one.
come again?
Repeat the question.
So what would we do if we can actually go to a planet, so one of the moons around Saturn that could support life? Well, I'd say there are 2 parts for 2 answers for this question. One of them is that even if it's support life, is going to support like basic form of life, and it might not be very good for us to live there. I mean, Mars would be much better and much easier to get there. But I am, as much as space explorations and I know establishing colonies on other planets is inspiring and everything, I'm completely against it personally. I don't like Elon Musk. Are we recording? He's gonna sue me now. And I don't like the plans of going to Mars just because we have a planet that can support life just so good. And what we're doing is that we are destroying it to get the resources to go colonize another planet that is completely uninhabitable. Maybe we just like live here and stop this greedy space race and.
Okay.
Oh, sorry.
Well, it will be around a couple more minutes
Sure.
if there's some people that have questions. But I think we'll, being it's 8:30, we'll end at that point, except to say there'll be a little afterglow because here we are almost 2 years later, renewing